Hi everyone, my name is Bryant Park, and I worked in Group T4J along with Crystal Shi, Lisa Lee, and Mahati Andavalu on our ECE6775 final project, which was accelerating convolution-based image super resolution. And our advisor for this project was Professor Zhu Zhang. To start, image super resolution is the process of taking an existing lower resolution pixelated image and transforming it into a higher resolution, finer detailed and sharper image. And so what we did was we implemented a software baseline for this image super resolution process. And this consisted of upsampling, then convolution and ReLU layers. And then we made this design synthesizable for the FPGA. And finally, we leveraged HLS optimizations to improve throughput for our upsampling, ReLU, and convolution layers. And we also evaluated the effectiveness of our designs. So as a baseline, we ran our software implementation on ARM architecture, which was on the Z board, and the x86-64 architecture, which is on ECE Linux. And we also compared between our unoptimized initial hardware design versus our optimized hardware design. And we ran those hardware designs on the Xilinx Zinc 7000 programmable SoC, which is embedded on the Z board. So talking more about implementation, we wrote for the accelerated version a host program that runs on the Z board. So the host program will load an image and then send it into the accelerator and receive the output image out from the accelerator. Within the accelerator, we have upsampling, convolution, and ReLU modules, which perform these operations on the image. And then the accelerator will output the image back out for the host program to receive. And so first we upsample, which involves just scaling the image by a factor of 2. And then we convolve the image with the 5x5 edge sharpening kernel. And we also pass the image through a ReLU filter. And this is a relatively simple image super resolution algorithm. And we settled on this one after researching a lot of alternatives because a lot of these more modern ML-based image super resolution algorithms have very, very large layers with that consist of too many weights to fit on the memory of the FPGA. And we also did process each RGB color channel separately, giving us some opportunities to parallelize execution.
Everyone, this is Mahati. Building on the baseline design presented earlier, let's discuss more on the optimizations we have implemented to enhance the performance and efficiency of our core functions. The optimizations focus on fixed point arithmetic, array partitioning, and loop transformations, each contributing significantly to our overall performance. Firstly, we have adopted a fixed point arithmetic representation with a 20,2 format for our pixel data. Since our pixel values range between 0 and 1, we only require two integers bits to capture this accurately. This precision is sufficient for our application and allows us to eliminate the overhead associated with floating point arithmetic. This way, we could achieve faster computations and reduced resource usage. Next, let's talk about array partitioning. Here, we have used both complete partitioning and cyclic partitioning. For the third dimension, which represents the RGB channel, we employ complete partitioning. This allows simultaneous access to all three channels, red, green, and blue, enabling parallel processing and reducing access latency. For spatial dimensions, we've implemented cyclic partitioning with a factor of 10. This means that the second dimension of our arrays is divided into subarrays with a stride of 10. This approach facilitates parallel access to spatial data, minimizing resource contention and enhancing throughput. Finally, we've also used loop transformations for our channels and kernel operations. By unrolling the loops over channels and indices, we enabled multiple operations to be executed in parallel with a single iterations. For example, in the convolution and ReLU function, the chan, ki, and kj loops are fully unrolled. This parallelism drastically reduces the computation time uh, by leveraging FPGA's capabilities. And for the outer loops, such as rows and columns in upsample and convolve and ReLU functions, we've applied pipelining. This technique overall overlaps the execution of consecutive iterations, ensuring that a new iteration can begin before the previous one is completed.
So now to get into some of our timing results. So we had our like estimated Vivado reports from like the synthesis and then also our like implemented FPGA runtimes. And so when we did synthesis in Vivado, we expected a 21 times speed up in estimated latency in Vivado. However, when we actually implemented this on the boards, only led to like about a 5 times speed up. And some factors that could be going into this could be like because of how things are specifically set up on the board, it might be like causing like extra delays and things like that. Um, and additionally, we found that our optimized design had a higher estimated clock, likely due to additional logic from optimizations. So it's not able to run at as fast of a frequency as our baseline design. For our utilization, we found that our optimized design took up way more area than the baseline. Um, and we were really struggling with this when we were trying to implement our optimizations because we were often running out of LUT usage if we tried to do things like unrolling our loops or like pipelining too much. Um, and so we've also been running into issues with VRAM when we try to scale up to 100 by 100 images. So we're working on implementing a FIFO in order to help with that, which we'll get into a little bit more later. Um, but yeah, BRAM and LUTs were two of the biggest usages of area utilization for us that we struggled to get to keep on the chip. So here's an example of what our super resolution results look like. So you can see on the left is a 20 by 20 image, and then on the right is a 28 by 28 image. Of like the same image that has been like super resolution. So essentially like it's a lot sharper, right? And so you can see like the edges are really sharp. There's a lot of like pixels that are also, as you can tell, like there's a lot of like white and blue interleaved where it like shouldn't really be. But it's hard to get like really good results with such a small image. And there are like you can see like greater results with greater image sizes, which is what we're trying to achieve. So here's like an example of like an 100 pixel image turning into a 200 by 200 pixel image. And so you can see on the left, like the fox is very blurry. But then on the right side, we can see that like the whisker is sharpened a lot. You can start to see some of the fur texture. And so this is kind of what we're aiming for in our next couple of optimizations. And now I'll go into the demo. So you can see here, I just finished running the Vivado synthesis, and you can see that our output is right here. This is our output image.txt. So this is our visualize.py, and this allows us to visualize our images. So you can see here, when I put in the input image, it'll pop up with a little window showing exactly what it looks like. Um, and so here I also have the output that is generated by the Vivado. And so this is the result of the Vivado over here. And so if we copy it over into the visualization, oh, oops, over here. And then over here we can change. So then we hit run and then we get this. which is exactly the image that I showed to you on the slide. You can see around here there are like these black borders. That's like the padding rows that we added. And so in our like when we get this image out, we could just like remove the padding on it afterwards. So that's a little demo, and now I'll pass it back on to Brian in order to go over our limitations.
Unfortunately, our current design has a limitation in which our maximum image size before the design becomes unsynthesizable is around 20 by 20 pixels. And this is because the board has a limited amount of VRAM and we store multiple image buffers for each layer. And each image buffer is around 40 by 40 pixels with 3 channels for each color per image. And so, as you can imagine, this ends up being a lot of memory usage, especially as the input image size goes up. Um, and another issue is that our output image is 28 by 28 in resolution. So we do have a scale factor of 2 for the upsampling, bringing the image from 20 pixels per side to 40 pixels per side. But we do lose 4 pixels per convolutional layer with the 5 by 5 kernel. And we have 3 convolutional layers, so we have to subtract 12 from the output resolution. And so the benefits of our super resolution algorithm actually aren't seen very clearly at lower image sizes, as you can probably tell from the previous slides. However, at larger image resolutions, our algorithm becomes more effective. And one workaround is that we can support larger image resolutions by performing super resolution in our accelerator in 20 by 20 tiles. So this would involve our host program breaking up a larger image into 20 by 20 tiles, passing them one at a time into the accelerator, and reassembling the output at the end. However, we want to kind of make the accelerator design itself more scalable. So we've been working on a redesign of our acceleration process, which Lisa can talk about in the next section.
To address the limitations of the previous design, our next step was to redesign the accelerator by improving the data flow. Specifically, this meant converting the interfaces between modules to streams or FIFOs rather than having each convolution layer transform the entire image before passing it to the next layer. So this required enforcing some new restrictions on our program, such as the order in which each layer consumes and produces values, but this redesign is advantageous since it significantly reduces the VRAM requirement for our accelerator. Since we no longer need to store multiple copies of the entire image on the board at a time, this design can handle images of much larger dimensions. We implemented this using the HLS Dataflow pragma, which enables task-level parallelism via overlapping execution through the FIFOs. So this means that once enough pixels are received by a convolution layer, it can begin computing the output instead of waiting to receive the entire image. A key optimization that enabled this new design was using a line buffer to store the active pixels in each convolution layer, which we fused with the ReLU layer to avoid excessive layers and streams. So the line buffer reads in pixels in precisely the row column order that we maintain across each module, and it allows us to maintain a minimally sized window of pixels necessary to perform each convolution. This is shown in the diagram here with a 3x3 kernel, and our design, which uses a 5x5 kernel, operates similarly, but instead maintains 5 active rows at a time. So while our redesigned implementation currently works well for small images, one issue that we run into is that the FIFOs will fill and block for larger images, which is likely due to a mismatch in the processing rate between different modules. As a result, our next steps involve examining the coordination of reads and writes to the FIFOs, as well as potentially merging the convolution across the 3 color channels, which are currently separated, into a single operation. So once this is addressed, we anticipate our accelerator will be able to more easily scale to larger image dimensions. With that, thank you for watching.